Hi, welcome to SQL Bits. My name is Pedro Lopes. I'm a program manager in the Azure Data SQL Server team. And today, I'm going to talk to you about query plans. More precisely, how query plans are in fact a map and an invaluable tool to help us do query performance analysis and troubleshooting. But I'm going to also show you some investments we've done in tooling around query plans to make sure that the experience is more seamless and it's basically easier to get to a point where we get tangible results and tangible recommendations to move forward. We will start by defining what is a query plan. A query plan consists of physical operators that implement operations described by logical operators. Those logical operators are in essence representations of the query, the transact SQL statements that were written by a user. The order of the operations is determined in the query plan and how data is joined, the sequence of the operations. So those are commonly known as the plan operators. The estimated row counts, the costs for each step, the actual row counts, the use of temporary objects such as work tables or work files in TempDB. Or if you're doing aggregations, how will the data be aggregated? At which stage of the execution? Is it using parallelism or is it running serially? And at the end of the execution or during execution, do I have warnings that I need to correct in order to improve performance or efficiency? And at the end of all the execution, I have query execution statistics that allow me to really get to a point where I understand what happened and then make educated decisions to fix or address performance issues that I may be experiencing. So all of this and much more is what we're going to discuss in the next 50 minutes in this session about query plans. Let's start by seeing how we can access query plans. One such option to access query plans is to prefix your query execution with show plan text on. This returns basic information for each of the statements without actually executing it. We see there a text-based order tree with all the steps involved in processing that query, including the type of join that will be used, the order in which tables are accessed, and even the indexes for each table. So it is a very basic representation that already allows us to see what executed in what order. Then there is show plan all. Show plan all returns more detailed information for each statement, but again without executing it. So it is in essence the same as show plan text, a text output tree, but then it adds additional columns with details on each of the physical operations that would be executed, such as the estimated number of rows, the estimated CPU time, the total cost estimations. So notice all the additional information that we have apart from the first column that we already saw in show plan text. Then we have show plan XML. This option produces the same estimated plan that we've seen in the previous two options, but as an XML output tree. Because it's generated as a link when I use it in SSMS, it can be interpreted by SSMS as a graphical estimated plan. Because remember, this hasn't been executed yet. So as such, it is the plan as it was created by the query optimizer and output and cached, and so it hasn't been executed yet. And before a plan executes, it is common to call it the estimated plan. Now, because it is a link, I can click on that link and it will display the graphical plan. The graphical plan is much more, it's just easier to consume. It's just easier to understand where each operation lies within this map that is the query plan. Show plan XML is also the option that's used by SSMS when we click the button Display Estimated Execution Plan. To access actual plans, it is a different option. An actual plan is the same plan as an estimated plan, only after being executed. And we can also use transact SQL commands or graphical tools to access those actual plans. The option Statistics Profile will return profile information for each statement, but now after executing it. Notice how it is also a text-based order tree. This shows you the same as showPlan all, incremented with the actual rows, as you see in the first couple of columns there, and the number of executions to display an actual plan, or query execution plan. The command Statistics Profile provides text-based information on query plans with different degrees of detail, as you see here. Using this command means SQL Server will actually execute the transactional statements and generate an actual plan, meaning it will take the plan that was created by the optimizer, which we called at that point the estimated plan, execute it, and it will then incorporate some runtime statistics as you see here. Another option is Statistics XML. This option is the actual plan counterpart of showPlan XML. Why? Because it generates a well-defined XML that can be interpreted by tools such as SSMS. And because it's generated as a link when you run it in SSMS, we can click on it, and as we do, we'll actually see a graphical representation of that XML. Notice that because it is a post-execution plan, what we call the actual plan, typically the arrow thickness will reflect the number of rows flowing from one operator to the next. Only that in this case, it's only one row, so it doesn't change. But we'll see more about that in a little while. Also notice how in the latest versions of SQL Server, it actually becomes easier to distinguish an actual plan from an estimated plan just by looking at it. Why? Because in an actual plan or in a post-execution plan, as you want to call it, each operator now has information about the elapsed execution time and a comparison between estimated rows and actual number of rows flowing through the operator. The estimated plan only has the estimated cost percentage there. And Statistics XML is the option used by SSMS when we click the button Display Actual Execution Plan. Under the covers, what it does is it will prefix the statement that you are about to execute with the Set Statistics XML on. There are other ways of accessing a query plan, additional methods. One that is available, but it is deprecated and you should not use, I cannot stress this enough, you should not use, is SQL Server Profiler, or server-side tracing, by the way. There are a number of extended events available that leverage normal profiling, and they can have a significant performance overhead. So most of these events should only be used when troubleshooting or monitoring very specific problems for brief periods of time. You see there are different text events that will return basically the query plan with slight differences in the amount of information that it retrieves. It is very similar to the several T-SQL commands that we've just seen. Each of the T-SQL commands would output a slightly different take on the same basic information, which is what data is accessed, how, and through which operators. So consider using these if you need to take a trace to analyze later, and really look upon the description of these events and make sure that you are using the ones that correspond to what we show here as lightweight profiling. There's also ways to access a query plan while it's still in flight. We've seen until now two different ways of accessing a query plan. Before it gets executed, the so-called estimated plan. After it gets executed, the so-called actual plan. But we can also access while it is being executed. For example, we can access it through Resource Monitor, and you see here an option called Show Live Execution Plan. I can right-click on the session that is running that I want to see the plan, and it will just display that for me. Another option is I have a query that I'm about to execute, and I want to see the live execution plan as it is executing. So I can do that by using the option in SSMS, include live query statistics. And when I use one of these two options, this is what I get. I get to see, this is an accelerated obviously, but I get to see the plan as it is getting executed already with information that I would only expect after the execution, which is the amount of rows that are flowing through the operators, the time that's being spent on each of them, and the estimated rows that were estimated for each of these operators. So what we call all these again, because we talked about what seem to be different plans, but they're not, they're all the same. The generic term, you can call it query plan, you can call it execution plan, you can call it show plan, but it's a generic term to signify that map, that tree that shows you all the information about what data is getting accessed, how data is being transformed through aggregations or joins, and how data is getting output. There are, however, different levels of detail that the query plan has depending on the option that you use. The plan that is immediately available after compilation is commonly known as the estimated execution plan, because that's a name that you see in SSMS. You can also call it estimated query plan. Why the word estimated? Because estimated means post-compilation, and compilation is based on cardinality estimations, based on statistics and some heuristics. So there's no execution yet, only information that flowed from the compilation stage. Then that plan, if you choose to, gets executed. And once it goes through execution, you can capture it during execution. And that you can see it commonly called the live plan, or the live execution plan, or even live query stats. All synonyms to signify looking at a plan with more details than it had just after compilation, because now it's already executing. It already has some runtime details, but it hasn't finished yet. There are a number of details that will only be available post-execution. Note that not all methods of accessing a query plan have the same overhead. Getting an actual plan, a post-execution plan, will always add overhead versus not capturing it. It's just that some methods that I've shown you today are more lightweight than others. When I was talking about the X events, I mentioned briefly something called the lightweight profiling versus a normal profiling. That is not only for X events, that's also for the other options that we've seen for capturing plans. That's a whole session on itself, so I'm not going to discuss that further. But if you want to get more details and really understand from all these options which are more lightweight than others, please visit that link on the screen there, because you'll get all the information that you need. Now that we've seen how to access a query plan, let's see how to read a query plan, namely a query plan that we have in a graphical format. So the flow of data is always read from right to left. And the thickness of the rows that flow through the operators will give you an indication of the number of rows in each dataset, like the one that's coming from the customer table clustered index scan on the lower right quadrant. We see this operator read 19,820 rows out of the exact same number of estimated rows. This is the best scenario that you can get. It's a 100% match. It means the engine had a perfect estimation for what it was going to read from that operator. For joins, the outer table will always appear on top, and the inner table will always appear, as the name suggests, on the inside of the join. Result sets are created from each join pair, which is then passed to the next join. And even in the actual execution plan, the percent cost that you see in each operator is still based on estimations. So do not use it as an accurate measurement of performance, because those still reflect the plan as it was created by the optimizer before being executed. During execution, you may hit bottlenecks and weights and other aspects that can affect the time it takes to run that specific operator, but also, if the estimations were incorrect, the number of rows flowing through the operators. So now that in more recent versions we have this information in line, the time per operator and the number of actual rows out of the number of estimated rows, use that information as a measure of performance. Here we have result set 1 and 2 being joined by the nested loops and then creating a result set 3. We also have a result set 4, which stems from that lower branch there, the inner side of the hash match. So result set 3 and 4 will be joined, creating a result set 5, which then is joined with result set 6, which is the clustered index seek there, to create the result set for the select clause. Joins producing smaller result sets are usually performed first. Local predicates can be applied before the join. It's called push-down predicates. And joins that reduce the number of rows are typically also performed earlier. All of this may not be exactly how we wrote the query, the order of the joins. But the optimizer will take all of this information into account and may actually reorder how it joins information to make sure it's more efficient and it reduces the row count early on. And how to access more information, a real treasure trove that is inside ShowPlan, inside our XML that we can't see immediately when we see the graphical format. So to access all the properties returned by ShowPlan and much more, you need to click the root node, so the select operator, right-click there, and click then on Properties. And we'll spend the next few minutes looking at some of these properties in greater detail so that we see what kind of insights we can derive from them. And this is just a sample of everything that's available. But we'll go through a number of properties that really allows us to create working hypotheses about query issues, query performance issues that we may be experiencing. For example, the list of trace flags. By accessing the properties of the root node, I can see a list of the active trace flags. And this is very useful to understand if there was any active trace flag that influenced the way that my query executed. I see there that I have a section is compile time true on the top, and that returns a list of all the trace flags that were active in the system when the query was undergoing the process of compilation and optimization. And then lower, I have the is compile time false section that returns a list of all the trace flags that are active in the system when the query is actually being executed. So if you see a different set of trace flags there, you should investigate the delta and which trace flags those are and if they had an impact on query optimization. For example, we immediately see that trace flag 9481 is present in the top list, which means it was present during compilation and optimization, but it doesn't have any bearing during execution. 9481 actually forces a specific model for cardinality estimation. So indeed, it has a bearing on how the query was compiled and optimized. So it may be very important for you to know this before you actually start doing more involved troubleshooting, because it may be a matter of trying to remove that trace flag and seeing after that how the query optimizer now creates a new plan for the same query under a different set of, let's say, rules and regulations of a different cardinality estimation model. So to recap, the top list will show me trace flags enabled at query compile time. So this list will be available in the so-called estimated plan. The bottom list are the trace flags active at query execution time, and these are only available in the post-execution plan, in the actual execution plan. Next, we have information about parameter types. Having this information here is very important in some scenarios. You may have conversion warnings, meaning that in your code, you are implicitly or explicitly converting one data type into the other, and that may pose issues around cardinality estimation, which then may lead you to have an inefficient plan. Now, if you have the statement in front of you, and typically the query plan has the statement, the query that you executed right there, it's easy to compare the body of the query with the parameter data type and see what conversion warnings happen there. But there are scenarios where we don't really have access to that source code, because all you see in your trace as you are looking at a plan is, for example, this sp execute. And this is executing previously prepared code. And if you have a pattern like this, that you prepare some queries that output a handle, and then it goes minutes without you actually executing that code. In the meantime, you may have thousands of events between these 2 points in time, between the sp prepare and the sp execute. And because with the plan you only see the sp execute, you're not able, as you see here, to understand what parameters were being used in the query itself. So, to be able to compare the text of the conversion warning with the parameter data type that now exists inside the query plan becomes much easier to troubleshoot these conversion warnings in these scenarios, rather than to try to make sense of a huge workload trace that may get difficult to find the appropriate source sp prepare. We also have inside the query plan information about times, namely the CPU time and the elapsed time to run a query. For example, we see here that the CPU time was about 91, almost 92 seconds, and we only have some few additional milliseconds in the overall elapsed time. This means that this query spent most of its time actively executing on the CPU. So with this information, we can already do a couple things. One, we can look for waits, which we'll see about it in a few minutes, and see if we have CPU-related waits. And also, we can look at the query plan and see if we have operators that typically drive more CPU usage. We'll also see about those later. And try to refactor the query or tweak the query in order to relieve this CPU time. We also have information in more recent versions about scalar UDF elapsed and CPU times. Scalar UDFs are very popular with developers because those are a mean to create reusable code. But the problem is, when you are referencing UDFs in a query, you may be facing hidden costs that can be detrimental to performance. It is like a cursor execution model, because a scalar UDF is invoked for each row that goes through your query plan, which means that because it is not part of the query optimization, it can render your query performance to a halt. In this example here, we see that the overall query took or spent 628 milliseconds of CPU, of which the overwhelming majority was actually spent executing the UDF. This is because while the internal execution of these functions is hidden in the query plan, you only see a execute scalar operator that has zero cost. And remember, the cost is always a compile time, an estimation of the possible cost the operator would have. But because scalar UDFs are not realistically costed, that means that SQL Server doesn't really account for the potential overhead of the code that you have inside the scalar UDF. So if you're using scalar UDFs, you now have this way of understanding how much is their relative overhead to your overall query execution. You can also see wait information. More recent versions of SQL Server, starting with 2016 as Service Pack 1, show you the top 10 wait types while your query was executing, and those get captured inside the query plan. You can then use that information to correlate, as I mentioned a minute ago, with the query times. For example, if I see a query that took 1 second of CPU of the 3 seconds of elapsed time, this means that the query was not active all the time. There are some waits occurring there. So I can correlate the overall query times with the waits and make use of other information that's captured in the query plan. For example, the degree of parallelism there. So I see that I have 1 second of CPU time. I have a degree of parallelism of 12, and I see that I actually waited on CX packet, which has to do with parallelism, almost 30 seconds during this entire query execution. So 30 seconds divided by the 12 threads. This explains, in part, the delta, the difference between CPU time and elapsed time. There were waits, there were times that the system was just waiting on something to occur. So the information, as you see here, the information inside the query plan already allows you to correlate and form working hypotheses about potential problems that you may be facing. The query plan also has information about memory usage. It includes extended information about memory grants per thread and per operator. So for example, if I look at these two data points, the granted memory and the maxed use memory, if those are very close to each other, that means that SQL actually used, for this query execution, actually used the memory it had estimated it would use. The granted memory is based on estimations, based on the estimated number of rows and the type of operations that the query will perform. The optimizer comes up with an optimal amount of memory for the query to execute. And in this case, we can see it's almost 800 megabytes. But then during execution, it ended up using a lot less than 1 byte, so it didn't even register here. That means that if there is this large skew in which the max use memory is a lot lower than the granted memory, this is hurting concurrency. Just to think in simple terms, think about a SQL server with 10 gigabytes of RAM, and that's also the max server memory. And now you're running queries that literally grab almost 800 megs of memory for each execution, but they end up using a lot less than that. But guess what? The granted memory means it's been reserved for that execution, which means for my 10 gigabyte of RAM server, I shouldn't be able to run more than, 10 queries of these at the same time? But as I see here, they actually need a lot less memory. So if I'm able to reduce that, I'm now able to run a lot more of these queries concurrently. In more recent versions, such as SQL Server 2019, you have a feature like memory grant feedback, which will adjust this automatically for you. If you're in an older version, you have more manual ways of dealing with this. But let's say, for example, that the granted memory was not enough. That originates spills to TempDB, which also hurt performance, but by creating bottlenecks based on I/O. So this information about memory can give you a lot of insight to make informed decisions about how to better improve concurrency and also limit performance issues derived from spills in your workloads. And since we're talking about memory, there are a number of warnings related to memory that you may see in any given execution plan. For example, this warning right there that says that the query had to wait 40 seconds for memory grant during execution. And I know this query took 42 seconds to execute. That means that literally it stood there for 40 seconds doing nothing. This warning ties directly to resource semaphore waits, which may indicate an excessive number of concurrent requests. So You already have a working hypothesis here. Maybe you need to have less workload or conversely, have more memory available. Other memory warnings also exist. For example, if there is an excessive grant, the scenario that we saw even in a more aggressive way a minute ago. Here I see that the memory grant was almost 70 megabytes, but the query didn't even use or used just around 1 megabyte. This is in itself an excessive grant. This means that the system is reserving a lot more memory than it's really needed to execute this query. If you are able to bring these numbers closer together, that means that you are opening yourself to running more workload with your existing resources, which means improving concurrency. This type of scenario can be handled in more recent versions of SQL Server and in Azure by the memory grant feedback feature. There are other warnings, such as other conditions for this warning. Grant increase or used more than granted. Grant increase you'll probably see in very intensive, memory-intensive batch mode workloads. It's only in batch mode that we allow potentially memory usage to slightly go above the initial grant. In row mode, that is simply not possible. You will spill. In batch mode, we try aggressively not to spill, so we have some leeway in which if the initial memory grant was not enough, the engine will allow the grant to grow up to a point. But if that happens, you'll see these type of warnings. This tells you that you have misestimations of memory. And whereas you would have this with row mode, you would spill to disk, you're not doing that as easily here. And if you have a lot of these concurrent queries grabbing more memory at runtime than they were granted initially, you may get into out of memory conditions. All of this information is in a query plan. So there's a lot you can derive from a query plan in terms of troubleshooting query performance conditions. The query plan also has information about spills. We've discussed briefly spills in this session today already. And spills we know that can be caused by memory misestimations. Having more insight into how much of an overhead a spill can be for my query is super important. For example, on the left side of the screen here, you see a sort spill. And you see that the sort spill wrote and then read over 4,400 pages from TempDB. You see on the right there a hash match that also had a spill, relatively small with only 32 pages. When we have this information, we need to ask ourselves questions like, is this spill relevant enough for me to go after? Does it consume too many resources? And in this case, I would say they do. If you are in a more recent version of SQL Server, like 2019, it has memory grant feedback feature, which would take care of this pattern automatically for you. The same goes with this other spill here. This is small enough for me not to really care about if I was executing this a handful of times. But if I'm executing this query dozens of times per minute, then the cumulative cost of so many small spills is noticeable. Again, if you are in SQL Server 2019 or in Azure, the system takes care of fixing these for you. However, if you are in older versions, you may need to take some more manual steps. We've seen a number of properties, and it's just a handful, just a sample of properties that are stored inside the show plan XML that allows us to create working hypotheses and to really understand both the context with which the query was running, but also some aspects that will allow us to take corrective actions. But we also invested in creating tools to analyze these query plans, adding a little bit more automation and intelligence around making sense of some of the information stored inside a query plan. One constant throughout all these troubleshooting scenarios has to do with comparing estimated rows with actual rows flowing through the operators in a query plan. This is because significant differences between estimated and actual rows usually expose cardinality estimation issues, which then speak to several possible causes, from outdated statistics to parameter sniffing, for example. With the plan open in front of you, such as this one that we captured from executing the store procedure USP sales tracking, we can right-click anywhere in the blank area in the query plan, and the following menu pops up. In this menu, I have an option which is Analyze Actual Execution Plan. So this only works with a post-execution plan. Analyzing the execution plan may also work in certain scenarios with the estimated plan, so the plan that you maybe retrieve from cache because it does not have runtime data, but typically you'll get much better results with a plan that also contains runtime data. So by clicking on the Analyze Actual Execution Plan, I'll be able to open a new window which is docked, which is called the Plan Analyzer. And immediately as it opens, it will position itself in the worst offender, let's say, in terms of inaccurate cardinality estimation. So I see here a Scenarios tab in the bottom window, and it already has in itself a child tab, Inaccurate Cardinality Estimation. This is, for now, the only scenario that's implemented, but it allows more tabs, so it is a placeholder to potentially add future scenarios if there's user demand for it. So if you find this useful, and if you would like to see more scenarios being exposed here to help you troubleshoot query performance based on analyzing plans, please let us know. So we should always start by analyzing findings that are related to data reading operators, such as our seeks and our scans, which is exactly where the tool positioned itself in the plan. And then we move up the query plan tree to go to aggregates and joins and analyze those. In this case, we see the clustered index scan in the plan for the sales order header bulk table as almost 13,000% difference between the actual rows and the estimated rows. The engine estimated that 1.5 million rows would be read from that operator, but in fact, only 11,927 were output. Notice that the finding details on the right. In this case, the analyzer could only find two possible reasons for this misestimation. The first reason, as you see there, is that the plan analyzer found a predicate in the scan that depends on a parameter, whose runtime value is different from the compile time value, because the plan also contains this information. Clicking in the link at the end of the finding, the word here, as you see, it says hyperlink, opens a pop-up window with more detailed background information about bad parameter sniffing and how to mitigate this, because this is essentially the description of a parameter sniffing sensitivity issue. The second finding there is about bad statistics. It's asking me to look at whatever statistics were loaded for this plan and verify whether they need to be updated or whether there's some other reason they may be inaccurate. Inaccurate statistics, outdated statistics will have a huge impact in the quality of your plan. So again, clicking the link at the end of the finding, the word here, will open another pop-up window with background information that is specific for that finding detail. It's very easy to determine how much of an issue the second one may be by using the actual execution plan like we have in this case here. So I could just click on the root node, the select there, and I would go into the properties, and I will look for the properties that you see here, the optimizer stats usage. I see that three statistics were loaded, And statistics through 2 and 3 are for the table of the operator in scope here, which is the sales order header bulk. As I can see here, the statistics do not need updating from a modification counter perspective. There's been no data modifications here. The modification count is 0. However, several statistics, 2 of them related to this table, were only created or updated last time with 6.6% sampling. If this is a big table, this may be an issue. So if it's possible to update statistics with a higher sampling ratio, that would mean that we would likely have a more accurate understanding of the data distribution based on that statistic, and then potentially the optimizer could do a better job. If the data distribution is not uniform, having a low sampling ratio will most likely skew statistics. So if you can update with a higher sampling ratio, even a full scan if possible, that would always be a good choice conceptually. However, if updating statistics with the largest sample is not doable for now, maybe these tables have millions of rows, and updating that with the largest sample could cause problems for my workload, we can go back and look at the other possible reason and suggestion there that pointed to bad parameter sniffing. So I go back to the query analyzer, and the first scenario here, the first finding detail, is also easy enough to investigate. I can, again, open the properties window from the root node and look at other parameters, namely the parameter list property. So if I look at the parameter list property, I see that the start order date parameter was compiled with the date 2011, so 31st July 2011. And that means that the first time this plan was compiled and then cached was optimized for this date value, this parameter. But however, this is not optimized for other executions. We see there that the parameter runtime value for the plan that I'm analyzing, that I've determined that it's not operating, let's say, at peak efficiency, is a different date. And this different date would likely have a better plan if it had been compiled specifically for it. Also note the query time stats. I will always be able to keep those in mind for a comparison perspective as I tweak this query and as I move along in my query troubleshooting process to see if I'm actually getting gains both in CPU time and in the elapsed time of my query. So I can do the following. I can test this parameter sensitivity issue, for example, creating a sort procedure on the side that it's the same. I just give it a different name, _test, as a suffix there, because I know that that won't be called by the application. And I will execute this new store procedure with the more recent date. And I can see that it yields a very different plan. This plan is very different from the one I saw earlier. For instance, it executes in parallel, and it has different join choices, for example. So for now, we have a few choices, such as using the query hint option recompile or optimize for unknown. And if I do that on the original store procedure that the application calls, I'll be able to have a more accurate plan for each of the incoming parameters. However, if I already know that the bulk of my executions are optimized with a given parameter, I can even use the optimize for query hint to make sure that it always gets compiled with that parameter that serves the bulk of my calls. And that will be detrimental for the parameters that are less used, but I have a sense of more stability in what relates to the plan that is generated. There are a number of operators that you would need to keep in mind when analyzing a query plan. Each icon visible in the query plan is an operator, and each of those physical operators will represent a task that needs to be done to complete the query, right? Accessing data, joining data, sorting data, for example. So I urge you to go to these links here and look at the some operators that support these fundamental data operations, accessing data, joining it, and sorting it. These are especially relevant to understand how to write good T-SQL that scales well if you're able to make sure that the engine makes the best choices around seeks and scans, around the types of joins being used, around whether I'm using sorts or not. For a complete reference, you should see the link on the screen there. And shameless plug, I've published a book together with my friend Pamela Hood, and we have a couple of chapters just dedicated to this, and you have the link right there. But alas, you don't have time to go through some detail today. Now, let's get to the final part of our session. There's some mythbusters I'd like to go over with you. Some questions that are fairly recurrent, and I know that likely through our own fault have created some confusion out there regarding this topic of query plans. So I tried to put them in sort of questions and answers right here to try to make it clearer. We've seen today about how to access the query plan in its various stages. So I think we can answer this first question by now. How many query plans can be cached at a single point in time for a query? Well, just one. There's only one plan. There's no more than one plan. Can a query have an estimated execution plan and a different actual execution plan? No. The query plan that's the output of the optimizer that gets cached, it's the plan that's going to be executed at some point in time, unless it later gets recompiled or it's evicted from cache and then has to be created again. But while that plan is cached, that is the one that's going to get executed. That means that it's the estimated execution plan, the ones that's post-compilation. If we look at that post-execution plan, we'll see that it has the same shape, the same operators in the same order. So it is the same plan. It has the same query plan hash. It has the same query plan handle. But now also has runtime statistics, metrics, that were only available either during execution or just after execution. And that is the actual execution plan. And we've seen methods today how we can capture a plan just after it executed. So why would I have a different actual execution plans in SSMS, or if I capture them through the several extended events that I have available? Again, that is still the same plan. However, we've seen that different events and even different transact SQL options will capture different degrees of detail for the same plan. It's still the same fundamental plan because all the operators are there in the same order, the same number of rows flows through the plan. It's just that the amount of runtime data will differ depending on the source that's used to collect it. We'll have X events that are more superficial, if you will, than others in the richness of the information that they collect. And what about the live execution plan? It's still the same plan. We just happen to tap into the plan after it got created and while it's still running. So it's not post-execution, it's during execution. It already has some runtime statistics and metrics that are available during execution, but not all of them, not all the ones that will be available post-execution. It's also known as live query stats. And does live execution plan require a cached plan? Yes, always. Only cached plans can be used or can be retrieved through the live query stats feature. But then another question comes to mind. I have statements that are very simple, trivial statements like insert into with values or create the index. Those aren't cached. We can't have live plans for those. That's another myth right there. All plans are cached for execution. The point is, some are not persisted beyond the immediate subsequent use. That's one case. The other case that may limit which plans you can see through live query plans versus ones that you can't see is actually the availability of that information, the query profile, as it's called. And this happens mostly with DDL. Why? Because there are certain types of statements that SQL Server internally converts into other operations. And those are the ones that are actually executed in lieu, so in replacement of the user written transact SQL. And because of that, that state for those internally converted queries doesn't get passed back into the parent caller. For example, alter index command. If you look at the plan of an alter index command, it is converted into an index insert command. This index insert command is executed outside of the user context. I've written altered index. That's the statement I sent in. The engine turns that into an index insert command. That is executed, but its runtime state does not get returned back to the parent handle, which is what I'm looking at through live query stats. So hopefully these myths are dispelled right now. There's a number of links I'd like to leave you with. You have demos around SQL 2019, intelligent query processing, and some of these tools that I mentioned today. Also, and again, the shameless plug, we have the book that you see at the cover right there. Feel free to leverage it, and it goes into a lot more detail on everything we discussed today, from internals of the query processor to patterns and anti-patterns in T-SQL that you want to avoid and strategies to avoid them. It also covers features that will automatically handle some of these scenarios for you, like intelligent query processor. If there's anything you take out of this slide, the last shortcut there, the one I call the one shortcut to rule them all, if you're a Lord of the Rings fan. If you remember that shortcut, you'll remember all the ones that are here and many, many more that go into obscure areas of the documentation that have information about internals and performance that is super relevant for you to keep in mind. But alas, those are too many URLs for us to remember. So keep that one in mind. Thank you very much and enjoy the rest of SQL Bits.